Now we are going to solve some of the problems in Smith chart. Okay, the first and foremost problem is a 30-meter long lossless transmission line with the characteristic impedance ZR equal to 50 ohms operating at 2 megahertz with the load impedance of ZR equal to 60 plus J40. If the velocity equal to 0.6 c on the line, find out the parameters, that is reflection coefficient, VSWR and the input impedance using Smith chart. Right? For this, first we need to write down the given values, right? So what are the values are given? The given values are load impedance capital ZR and the characteristic impedance capital Z0 and the length of the transmission line, that is 30-meter. In addition, the frequency is also given and the velocity is also given, right? So these are the parameter, right? For any Smith chart problem, first we need to find out the basic thing is called normalized load impedance, right? So the normalized load impedance is the basic thing we need to find it out. That is small ZR equal to capital ZR divided by ZR. So what is capital ZR here? That is 60 plus J40. 60 plus J40 and capital ZR is 50. So 60 plus J40 divided by 50 is equal to 60 by 50 plus J times 40 divided by 50. What is 60 by 50? That is 1.2 plus J. What is 40 by 50? 0.8 ohms, right? So this is the first value, small ZR value we need to find out for any problem. Next, we need to plot the small ZR point in the Smith chart, right? So this is the thing. Now I am going to do the same thing in this picture, right? So here 1.2, we need to find out 1.2 plus j zero point 0.8, we need to plot it, right? So for that, this is our typical Smith chart, right? So let me zoom out. So this is the typical Smith chart, right? So here in this Smith chart, what we are going to do is that this is our real axis, right? So we know that this is our real axis, okay? So this is our real axis, and in this we need to find out where the value 1.2 is there. So 1.2 is between 1 and 1 point. Here we can see this is 0, 0 0.1, 0 0.2. So 1.2 is here, right? So 1.2 is here, and here this is 1.2 where the value 0.8 is. So this is 0 0.1, 0 0.4, 0 0.5, 0 0.6, 0 0.7, 0.8, right? So now this is 0.8. So after that, you try to trace this 0.8 like this, okay? And 1.2 also you need to trace it. 1.2 is trace it like this, trace it like this, and this is the point small zr where the point 1.2 plus j point is intersecting, right? Next, for finding reflection coefficient, what you have to do is that we need to find out two things in reflection coefficient, right? So the first thing is we have to find out the magnitude of reflection coefficient. Next, we have to find out the phase, right? For finding the magnitude, what we have to do is that this is nothing but the center point. Always this is going to be the center point or matching point or tuning point, right? From the center point, the using EZR, right? From the center point, EZR from center with ejecta, right? So with this, make a arc in the compass, right? From ejecta towards the center, make a arc, right? So take that arc and we have to interpolate that arc in the radial scale parameter under reflection coefficient VOL. VOL is there, power is also there. In the radial scale parameter, that arc has to be, here we have that arc, no, this arc, right? So from center to this small zeta, that arc has to be cut it over here, right? So we have to make an arc like this, okay, in the VOL scale, right? Already I told you the radial scale parameter, this is the center, this is 0 and this value is 1. In between you have to look at 0 0.1, 0 0.2, 0 0.3, 0 0.4. Now the value is intersecting at 0.38. So 0.38 is the magnitude, right? Next, we need to find out the angle. That is very easy. What you have to do is that for finding angle from the center towards ZR, draw a straight line like this and extend it outwards, right? So now we have to look at the angular reflection coefficient, right? So we have to find out, we have to look at the angular reflection coefficient, that is here, angular reflection coefficient, right? So here the value is 0, 10, morning itself I told you, right? 0, 10, 20, 30, 40, and this is 50. So now the value is 50, 52, 54. So the value is somewhere around 55. So 55 degree is the angle, right? So now by plotting, so yeah, I'm going for method 2. So with the radius OP, right? So OP is nothing but this one. The small z I have marked, no, this point is P, right? So this is origin is plotted as O, right? So OP with the radius OP, make an arc on the radial scale parameter, which is located at the bottom. That is what I done it, right? So make arc on the reflection coefficient in voltage scale, right? So make arc on reflection coefficient in voltage for scale. For angle calculations, right? And that value, draw the straight and find the value which center the magnitude towards the zeta point and look at the interior scale of the angle reflection, right? So there the value is 55. So now the reflection coefficient value tau equal to 0.35 in magnitude and 55 in angle, right? So next we have to find out the VSWR, right? So that is very easy. For finding VSWR, what you have to do is that from the center, using zr as the radius and 1 comma 0 as the center, you have to draw a circle like this. Okay, so you have to draw a circle like this. Okay, so this is the circle. Okay, so I think. Okay, so this is our circle. Right, so this circle is nothing but the VSWR circle. Whenever you are drawing 1 comma 0 as the center point and small z as the radius, this is VSWR circle, right? Now this VSWR circle, where it intersects the real axis is nothing but the rightmost part of the real axis. The VSWR circle will intersect at one point at the RHS of the real axis, right? That value will be the that value will be the VSWR value. So now here the value is intersecting at 2. Here the value is 2.1. So the value of VSWR is 2.1, right? So this is how we have to find out the VSWR value, right? That is what they're doing it here, right? Get off it, right? So next we are going to compute the input impedance, right? For finding the input impedance, first we need to find out the lambda, right? So what is lambda? Lambda equal to C by F. So but here the C value is not given. Instead they are giving the velocity of light, that is 0.6 C they have been given in the problem, right? Initially they are given the velocity as U equal to 0.6 C. So lambda equal to U by F. So 0.6 C divided by F. So zero point 0.6 into 3 into 10 power 8 divided by F is frequency is 2 megahertz. The frequency is 2 megahertz. So that's why 2 into 10 power 6. So 2 into 10 power 6. So lambda equal to 90 meter. So 1 lambda here length is equal to 30 meter. 1 lambda equal to 90 meter. Then now we need to represent length in terms of lambda. L in terms of what? Lambda. So 1 lambda equal to 90 meter. Then how many lambda equal to 30 meter? That 30 divided by 90 meter times lambda. So L equal to 0.33 lambda, right? So now we need to find out the input impedance 0.33 lambda distance from the load, right? So that is what the objective, right? So that means we need to move towards the generator or we need to move away from the load, right? We need to move towards the generator with the distance of 0.33 lambda on the point, right? So by doing this, so we are getting some values of small z. Let me do it, right? So for this, what they are telling is that here you can see this is the value, right? So here the value is 0 point somewhere 0.17. So you have to look at wavelength towards generator scale, right? So wavelength towards generator scale, the value is here, the value is 0, 0.1. Wavelength towards generator, this is 0.1 and this is 0.2, right? Like 0.01, 0.02 likewise, right? So now wavelength towards generator scale, what is the value here? 0.15, 0.16, 0.17, 0.18. So this is between 0.17 and this. So 0.17, 2 points is behind. So can I assume 0.174, right? So this 0.174 lambda has to be added with 0.33 lambda. So now 0.33 and this is was what? 73 is 0 plus 1. So 0.504 lambda, right? So you know that where the value 0.504 lambda is, right? So this is 0 lambda and this is 0.25 lambda. And if you want to come again to the same place, that is 0.5 lambda. 0.50 lambda is 0.5 to 0.51 lambda, between 0.5 and 0.51. Why I am calling this is 0.51? Because I complete one revolution. After that, this value become zero point 0.5, 0.51, right? 0.52, 0.53. Likewise, this value will become 0.75. Like that, it will change. Okay. So because I am completing one revolution. Now, where the value 0.504? This is zero point 0.5. This is zero point 0.5. You have to take 2 points, right? So from that, you need to draw a straight line towards the center point, right? So from this, you have to draw a straight line towards what? The center point, like this. Okay. Now, here there is a value. Here, this is the intersection point, right? So this is our intersection point where that line crosses with VSWR circle. This point is nothing but small hs, right? Now we have to trace this value in the real part and you have to trace that value also in the imaginary part, right? So by tracing it, so the real value is somewhere around zero point 0.6 and the imaginary value is somewhere around 0. So you have to look at the interior part of reactor. So 0, 0.02, right? So now that's how they'll be plotting and they are getting the values 0.47 in the real axis and 0.035 in the imaginary axis, right? So this is small hs, but our job is to find out capital hs, right? So for that, we know the small hs equal to capital hs divided by z naught. So capital Z is equal to small z is into Z naught. So 0.47 plus J 0.035 into 50 ohms, that is 23.5 plus J 1.75 ohms, right? So this is how we have to find out capital ZS. Okay, thank you guys.